Now, our today's topic is about Ohm's law. We have already discussed the terminologies of current, voltage, and resistance. So, after this, we need to uh, discuss Ohm's law. So, you can see a circuit diagram here in which we have different components connected with each other. The first is battery, low voltage supply. It's a symbol of a battery, a variable resistor, a resistor that is used to vary current in the circuit, a voltmeter, and a nichrome wire of high resistance, and a thermometer that is used to measure the temperature of water, and an ammeter and a switch, right? So the circuit below can be used to investigate how current through a conductor depends on the potential difference. We will get to know that what is the relationship between current and voltage, right? Current means I and voltage means V. We need to discuss the relationship between both these formulas. The conductor in this case is a coiled up length of a nichrome wire kept at constant temperature by immersing it in a large amount of water. You can see in the diagram, Daniel, that we have used this nichrome wire and we kept the temperature constant, right? And this coil is completely immersed into the water, right? So potential difference across nichrome wire can be varied by adjusting variable resistor. Typical results are shown. You can see in the diagram, you can see in the table, after 1 volt, 1 volt, the current would be 0.2 amperes. After 1 volt, it becomes 2 volt now, and the the current would be 0.4 amperes. After 1 volt, 3, then 0.6, 4, then 0.85, then 1. Right? And we can see the value of the resistor is constant in every case. Right? It would be 5 ohm. Right? So after the increment of 1 voltage, 1 volt, the current would increase up to 0.2 amperes. So for the when the 1 volt increase, the current would be increased to 0.2 amperes. So as current increases, as voltage increases, current would also increase. So we have a linear relationship between current and voltage for Ohm's law. We will be discussing its statement later. So this is the origin, right? The x-axis for the voltage and the y-axis for the current. So for 1 volt, the current would be 0.2. For 2 volt, the current would be 0.4. For 3 volts, and is 2.6. For 4 volt, it would be 2.8. For 5 volt, it would be 1. So we can join all the marks and it becomes a linear graph, right? So the result in the table shows that when the voltage increases, the current also increases within a constant temperature. This would only happen, Daniel, when the temperature is kept constant. If the temperature is not constant, it varies, so then it will not be a straight line, right? So it will only happen when the temperature is kept constant and the gradient of the graph is constant value. Voltage divided by current is equal to the constant value of resistance. We discussed yesterday for resistance, we would divide the value V over I so that we conclude under the constant temperature, voltage is directly proportional to the current. This is called law. Some कहते हैं Ohm's law, right? So The resistance of most of the conductor becomes higher if the temperature of the conductor increases. If the temperature increases, it is not constant. If it increases, so automatically the resistance would also increase. The temperature increases, the resistance increase. As the temperature rises, the metal ions vibrate more and provide greater resistance to the flow of electrons. For example, take an example of filament lamp, right? As the current flows through the filament lamp, it gets hotter. Again, when it gets current, the temperature of the filament increases and it becomes hotter. So now the resistance will also increase. This means the current varies with the voltage is not directly proportional, not give us a straight line for the current voltage graph. Look at the graph for the filament lamp. Because of the change in temperature, the graph would be like this. For some time, it becomes straight, but when the temperature starts to increase now, the graph would be like this. It becomes curved. So always remember this. It is a graphical representation of the filament. So the statement of the Ohm's law would be like this. The potential difference across any metallic conductor is directly proportional to current provided the temperature of the conductor is kept constant, right? So the equation would be V equals to IR, voltage equals to current multiplied by resistance, right? So far, any confusion? Daniel, hello. Daniel, can you hear me?
Your
Hello.
voice was lagging. Yeah, I can hear you.
Any confusion about it?
No, till now it's clear.
Okay. Now, there are some resistor which depends on the intensity of light, and those resistors are called LDRs, right? Light dependent resistor. A light dependent resistor is a type of a variable resistor whose resistance depends on the amount of light falling on it. It will look like this. The electronic symbol is like this, and in a real view, it looks like this. So it's made up of semiconductor material called cadmium sulfide, right? In the dark, LDR has high resistance, often over 1 mega ohms. However, light can provide energy needed to allow a current to flow. Shine light on the LDR and its resistance increases. As the intensity of the light that is falling on the LDR increases, so the resistance of the LDR would decrease, so a current can pass through it. But in the case of a darkness, there is no light, then the LDR's resistance would be very high, and the small amount of current can pass through it. So in bright light, the resistance may fall to 400 ohms. LDR uses circuit to detect the level of light. For example, in security lights that switch on automatically at night. Right? Got it?
Yes, it's clear.
Okay. Now, how we connect resistors in series? So, as I told you in the first two lectures, that in a series arrangement, the uh, circuit would be like this. So the circuit would be like this, means it's, it's, oh, it's 2 on, it's 8 on. the total resistance would be R1 plus R2, 2 plus 8 would be 10, right? So we can directly add the values and get the total resistance. Okay. Now in parallel, how we can add the 1 over R1 plus 1 over R2 plus 1 over R3. So in parallel, we would be the circuit would like this 1 over 2 plus 1 over 5 spark plug filling, and the value of the total resistance would be 1.343. So in parallel, the resistors would be connected like this, and for the uh, circuit in series, the resistor would be connected in a line, a single line, right? So this is how we can connect. I would like you to solve this one. The time starts now.
Okay, I got 1 over 5. Wait, no. Yeah, I got 1 over 5 somehow.
Yes.
Isn't it like
What?
1 over 10 plus 1 over 10 like this?
1 over 10 plus 1 over 10, it would be 2 over 10, right? So 1 over 5.
Yes.
And
Yeah.
for the resistance value, it would be total resistance R would be equals to, right?
Yeah.
So for the DC circuits, series circuit would like this. We have two resistors, 6 ohm and 4 ohm, and the battery is of 16 volts. So when the resistor or the other components are connected in series, the current at every point in the circuit is same. The current would be same because in series, current is same, potential difference is different in series circuit, right? So first of all, we need to calculate the total resistance. So R1 plus R2, 10, 6 plus 4 equals to 10. We want to find out current in a circuit. Uh, so we will use the formula I equals to V upon R. So 16 divided by 10 would be 1.6 amperes, right?
Yes.
But when we are talking about series circuit and we need to find out the potential difference on every resistor. So what would be the formula if current is same on both? So 1.6, 1.5 will be appearing on both the resistors. So because it's a series circuit, but the potential difference will be different, depends on the value of the resistor. So V equals to IR. So because of the value here is 6 ohm, which is greater, there will be large potential drop on this particular 6 ohm. So 9.6 volt is dropping here, and 6.4 volt is dropping on 4 ohm. V equals to IR is 9.6. 6.4. Got it? So we need
That's
to
clear.
recheck either the voltage that we have found is correct or not. So we can add both the vectors, which will be equal to the EMF of the battery, which is 16 volts. It means that our calculation is correct, right? So this is
Yeah.
about a series circuit. Now for parallel circuits, we have two resistors, 8 ohms and 2 ohms with a battery of 18 volts. So in parallel circuit, current would be different. Current is different. Voltage is same. Voltage would be equal to the EMF of the battery, which is 18, right? Got it?
Yes.
So the current across 8 ohm would be 2.25 ampere. 18 divided by 8. 18 divided by 8. And on the 2 ohm resistor, the current would be 9. The sum of the current and separate branches would be 11.25 ampere and is equal to the current from the source. Got it?
Yeah, this is clear.
So advantages of connecting electrical components in parallel. There are some advantages of connecting lamps, right? The voltage to each lamp is same, so each lamp has the same bright. If one lamp is melted, the other lamp will work, but in series, if one lamp melts, other will not work, right? So it's the main advantage of connecting components in parallel. These are the electrical symbols of different electronic components. These are the lamp, ammeter, meter, switch, cell, several cells, AC power supply, DC power supply, variable resistors, light dependent resistor, fuse, diode, light emitting diode, magnetizing coil, electric bell, relay, right? So these are the whole electronic symbols of different electronics. So draw a circuit diagram including a 1.5 volt power supply of fixed voltage. So we have drawn this one bulbs are connected in series. Switch here, the switch, right? An ammeter to measure the current through the circuit, so it must be connected in series here, series, and voltmeters across each one to measure the potential difference across the path. Right? Tasks to do.
Okay.
You have to draw a circuit diagram. 15 volt power supply, fixed voltage units are connected parallelly, creating 5 ohms, a switch and ammeter to measure the current through the circuit and the variable resistance. Right?
Yeah.
So Alhamdulillah, we have completed this whole chapter today.
Oh, yes. Fine.
The Any question about it? Any question about it,
No,
Daniel?
till now it looks clear.
No, clear, clear. So wait a
No,
minute.
not till now.
Uh, Daniel, from the syllabus, we have completed 4.3.2, right? You can check
Oh yeah, I'll
also.
check as well.
4.3.2 we have completed.
I'll also check.